Brought to you by WikiVidi.com. Moon. The Moon is an astronomical body that orbits planet Earth, being Earth's only permanent natural satellite. It is the fifth largest natural satellite in the Solar System, and the largest among planetary satellites relative to the size of the planet that it orbits. Following Jupiter's satellite Io, the Moon is second-densest satellite among those whose densities are known. The Moon is thought to have formed about 4.51 billion years ago, not long after Earth. The most widely accepted explanation is that the Moon formed from the debris left over after a giant impact between Earth and a Mars-sized body called Theia. The Moon is in synchronous rotation with Earth, always showing the same face, with its near side marked by dark volcanic maria that fill the spaces between the bright ancient crustal highlands and the prominent impact craters. As seen from the Earth, it is the second-brightest regularly visible celestial object in Earth's sky after the Sun. Its surface is actually dark, although compared to the night sky it appears very bright, with a reflectance just slightly higher than that of worn asphalt. Its gravitational influence produces the ocean tides, body tides, and the slight lengthening of the day. The Moon's average orbital distance at the present time is 384,402 kilometers or 1.28 light seconds. This is about 30 times the diameter of Earth, with its apparent size in the sky almost the same as that of the Sun, resulting in the Moon covering the Sun nearly precisely in total solar eclipse. This matching of apparent visual size will not continue in the far future, because the Moon's distance from Earth is slowly increasing. The Soviet Union's Lunar program was the first to reach the Moon with uncrewed spacecraft in 1959. The United States NASA Apollo program achieved the only crewed missions to date, beginning with the first crewed lunar orbiting mission by Apollo 8 in 1968, and 6 crewed lunar landings between 1969 and 1972, with the first being Apollo 11. These missions returned lunar rocks which have been used to develop a geological understanding of the Moon's origin, internal structure and later history. Since the Apollo 17 mission in 1972, the Moon has been visited only by uncrewed spacecraft. Within human culture, both the Moon's natural prominence in the earthly sky and its regular cycle of phases as seen from the Earth have provided cultural references and influences for human societies and cultures since time immemorial. Such cultural influences can be found in language, lunar-based calendar systems, art and mythology. Name and etymology. The usual English proper name for Earth's natural satellite is the Moon. The noun moon is derived from moon, which developed from mon, which is derived from Old English mona, which ultimately stems from Proto-Germanic mnon. Like all Germanic language cognates, occasionally the name lunar is used. In literature, especially science fiction, lunar is used to distinguish it from other moons, while in poetry, the name has been used to denote personification of our moon. The principal modern English adjective pertaining to the Moon is lunar, derived from the Latin luna. A less common adjective is selenic, derived from the ancient Greek selene, from which is derived the prefix seleno. Both the Greek Selene and the Roman goddess Diana were alternatively called Cynthia. The names Lunar, Cynthia, and Selene are reflected in terminology for lunar orbits in words such as apollune, pericynthian, and selenocentric. The name Diana is connected to dies, meaning day. Formation. Several mechanisms have been proposed for the Moon's formation 4.51 billion years ago, and some 60 million years after the origin of the Solar System. These mechanisms included the fission of the Moon from Earth's crust through centrifugal force, the gravitational capture of a preformed moon and the co-formation of Earth and the Moon together in the primordial accretion disk. These hypotheses also cannot account for the high angular momentum of the Earth-Moon system. The prevailing hypothesis is that the Earth-Moon system formed as a result of the impact of a Mars-sized body with the proto-Earth that blasted material into orbit about the Earth that then accreted to form the present Earth-Moon system. The far side of the Moon has a crust that is 30 miles thicker than the near side of the Moon. This is thought to be due to the Moon having been amalgamated from two different bodies. This hypothesis, although not perfect, perhaps best explains the evidence. 18 months prior to an October 1984 conference on lunar origins, Bill Hartmann, Roger Phillips, and Jeff Taylor challenged fellow lunar scientists, "You have 18 months. Go back to your Apollo data, go back to your computer, to whatever you have to, but make up your mind. Don't come to our conference unless you have something to say about the Moon's birth." At the 1984 conference at Kona, Hawaii, the giant impact hypothesis emerged as the most popular. Before the conference, there were partisans of the three traditional theories, plus a few people who were starting to take the giant impact seriously. And there was a huge apathetic middle who didn't think the debate would ever be resolved. Afterward, there were essentially only two groups, the giant impact camp and the agnostics. Giant impacts are thought to have been common in the early solar system. Computer simulations of a giant impact have produced results that are consistent with the mass of the lunar core and the present angular momentum of the Earth-Moon system. These simulations also show that most of the Moon derived from the impactor rather than the proto-Earth. More recent simulations suggest a larger fraction of the Moon derived from the original Earth mass. Studies of meteorites originating from inner solar system bodies such as Mars and Vesta show that they have very different oxygen and tungsten isotopic compositions as compared to Earth, whereas Earth and the Moon have nearly identical isotopic compositions. The isotopic equalization of the Earth-Moon system might be explained by the post-impact mixing of the vaporized material that formed the two, although this is debated. The great amount of energy released in the impact event and the subsequent reaccretion of that material into the Earth-Moon system would have melted the outer shell of Earth, forming a magma ocean. Similarly, the newly formed Moon would also have been affected and had its own lunar magma ocean. Estimates for its depth range from about to its entire depth. While the giant impact hypothesis might explain many lines of evidence, there are still some unresolved questions, most of which involve the Moon's composition. In 2001, a team at the Carnegie Institute of Washington reported the most precise measurement of the isotopic signatures of lunar rocks. To their surprise, the team found that the rocks from the Apollo program carried an isotopic signature that was identical with rocks from Earth, and were different from almost all other bodies in the solar system. Because most of the material that went into orbit to form the Moon was thought to come from Theia, this observation was unexpected. In 2007, researchers from the California Institute of Technology announced that there was less than a 1% chance that Theia and Earth had identical isotopic signatures. Published in 2012, an analysis of titanium isotopes in Apollo lunar samples showed that the Moon has the same composition as Earth, which conflicts with what is expected if the Moon formed far from Earth's orbit or from Theia. Variations on the giant impact hypothesis may explain this data. Internal structure. The Moon is a differentiated body. It has a geochemically distinct crust, mantle and core. The Moon has a solid iron-rich inner core with a radius of, and a fluid outer core primarily made of liquid iron with a radius of roughly Around the core is a partially molten boundary layer with a radius of about. This structure is thought to have developed through the fractional crystallization of a global magma ocean shortly after the Moon's formation 4.5 billion years ago. Crystallization of this magma ocean would have created a mafic mantle from the precipitation and sinking of the minerals olivine, clinopyroxene and orthopyroxene. After about 3/4 of the magma ocean had crystallized, lower density plagioclase minerals could form and float into a crust atop. The final liquids to crystallize would have been initially sandwiched between the crust and mantle, with a high abundance of incompatible and heat-producing elements. Consistent with this perspective, geochemical mapping made from orbit suggests the crust of mostly anorthosite. The Moon rock samples of the flood lavas that erupted onto the surface from partial melting in the mantle confirm the mafic mantle composition, which is more iron-rich than that of Earth. The crust is on average about thick. The Moon is the second densest satellite in the Solar System after Io. However, the inner core of the Moon is small with a radius of about ls. Around 20% of the radius of the Moon. Its composition is not well defined, but is probably metallic iron alloyed with a small amount of sulfur and nickel. Analyses of the Moon's time variable rotation suggest that it is at least partly molten. Surface geology. The topography of the Moon has been measured with laser altimetry and stereo image analysis. Its most visible topographic feature is the giant far-side South Pole Aitken Basin, some in diameter, the largest crater on the Moon, and the second largest confirmed impact crater in the Solar System. At deep, its floor is the lowest point on the surface of the Moon. The highest elevations of the Moon's surface are located directly to the northeast, and it has been suggested might have been thickened by the oblique formation impact of the South Pole Aitken Basin. Other large impact basins, such as Imbrium Serenitatis, Crisium Smythe and Oriental, also possess regionally low elevations and elevated rims. The far side of the lunar surface is on average about higher than that of the near side. The discovery of fault-scarp cliffs by the Lunar Reconnaissance Orbiter suggests that the Moon has shrunk within the past billion years by about 90 meters. Similar shrinkage features exist on Mercury. Volcanic features. The dark and relatively featureless lunar plains clearly seen with the naked eye are called maria, as they were once believed to be filled with water. They are now known to be vast solidified pools of ancient basaltic lava. Although similar to terrestrial basalts, lunar basalts have more iron and no minerals altered by water. The majority of these lavas erupted, or flowed into the depressions associated with impact basins. Several geologic provinces containing shield volcanoes and volcanic domes are found within the near-side maria. Almost all maria are on the near side of the Moon and cover 31% of the surface of the near side, compared with 2% of the far side. This is thought to be due to a concentration of heat-producing elements under the crust on the near side, seen on geochemical maps obtained by Lunar Prospector's gamma-ray spectrometer, which would have caused the underlying mantle to heat up, partially melt, rise to the surface, and erupt. Most of the Moon's mare basalts erupted during the Imbrian period, 3.0–3.5 billion years ago, although some radiometrically dated samples are as old as 4.2 billion years. Until recently, the youngest eruptions dated by crater counting appeared to have been only 1.2 billion years ago. In 2006, a study of Ina, a tiny depression in Lacus felicitatus, found jagged, relatively dust-free features that, due to the lack of erosion by unfalling debris, appeared to be only 2 million years old. Moonquakes and releases of gas also indicate some continued lunar activity. In 2014, NASA announced widespread evidence of young lunar volcanism at 70 irregular mare patches identified by the Lunar Reconnaissance Orbiter, some less than 50 million years old. This raises the possibility of a much warmer lunar mantle than previously believed, at least on the near side where the deep crust is substantially warmer due to the greater concentration of radioactive elements. Just prior to this, evidence has been presented for two 10 million years younger basaltic volcanism inside Lowell crater Oriental Basin, located in the transition zone between the near and far sides of the Moon. An initially hotter mantle and/or local enrichment of heat-producing elements in the mantle could be responsible for prolonged activities also on the far side in the Oriental Basin. The lighter-colored regions of the Moon are called Theia, more commonly highlands, because they are higher than most maria. They have been radiometrically dated to having formed 4.4 billion years ago, and may represent plagioclase cumulates of the lunar magma ocean. In contrast to Earth, no major lunar mountains are believed to have formed as a result of tectonic events. The concentration of maria on the near side likely reflects the substantially thicker crust of the highlands of the far side, which may have formed in a slow-velocity impact of a second moon of Earth a few tens of millions of years after their formation. Impact craters. The other major geologic process that has affected the Moon's surface is impact cratering, with craters formed when asteroids and comets collide with the lunar surface. There are estimated to be roughly 300,000 craters wider than on the Moon's near side alone. The lunar geologic timescale is based on the most prominent impact events including Nectaris, Embrium and Oriental structures characterized by multiple rings of uplifted material, between hundreds and thousands of kilometers in diameter and associated with a broad apron of ejecta deposits that form a regional stratigraphic horizon. The lack of an atmosphere, weather, and recent geological processes mean that many of these craters are well preserved. Although only a few multi-ring basins have been definitively dated, they are useful for assigning relative ages, because impact craters accumulate at a nearly constant rate. Counting the number of craters per unit area can be used to estimate the age of the surface. The radiometric ages of impact melted rocks collected during the Apollo missions cluster between 3.8 and 4.1 billion years old. This has been used to propose a late heavy bombardment of impacts. Blanketed on top of the Moon's crust is a highly comminuted and impact-gardened surface layer called regolith, formed by impact processes. The finer regolith, the lunar soil of silicon dioxide glass, has a texture resembling snow and a scent resembling spent gunpowder. The regolith of older surfaces is generally thicker than for younger surfaces. It varies in thickness from in the highlands and in the maria. Beneath the finely comminuted regolith layer is the megaregolith, a layer of highly fractured bedrock many kilometers thick. Comparison of high-resolution images obtained by the Lunar Reconnaissance Orbiter has shown a contemporary crater production rate significantly higher than previously estimated. A secondary cratering process caused by distal ejecta is thought to churn the top 2 centimeters of regolith 100 times more quickly than previous models suggest, on a time scale of 81,000 years. Lunar swirls. Lunar swirls are enigmatic features found across the Moon's surface which are characterized by a high albedo, appearing optically immature and often displaying a sinuous shape. Their curvilinear shape is often accentuated by low albedo regions that wind between the bright swirls. Presence of water. Liquid water cannot persist on the lunar surface when exposed to solar radiation. Water quickly decomposes through a process known as photodissociation and is lost to space. However, since the 1960s, scientists have hypothesized that water ice may be deposited by impacting comets or possibly produced by the reaction of oxygen-rich lunar rocks and hydrogen from solar wind, leaving traces of water which could possibly persist in cold, permanently shadowed craters at either pole on the Moon. Computer simulations suggest that up to of the surface may be in permanent shadow. The presence of usable quantities of water on the Moon is an important factor in rendering lunar habitation as a cost-effective plan. The alternative of transporting water from Earth would be prohibitively expensive. In years since, signatures of water have been found to exist on the lunar surface. In 1994, the bistatic radar experiment located on the Clementine spacecraft indicated the existence of small frozen pockets of water close to the surface. However, later radar observations by Arecibo suggest these findings may rather be rocks ejected from young impact craters. In 1998, the neutron spectrometer on the Lunar Prospector spacecraft showed that high concentrations of hydrogen are present in the first meter of depth in the regolith near the polar regions. Volcanic lava beads brought back to Earth aboard Apollo 15 showed small amounts of water in their interior. The 2008 Chandrayaan-1 spacecraft has since confirmed the existence of surface water ice using the onboard Moon mineralogy mapper. The spectrometer observed absorption lines common to hydroxyl in reflected sunlight, providing evidence of large quantities of water ice on the lunar surface. The spacecraft showed that concentrations may possibly be as high as 1000 ppm. In 2009, LCROSS sent a impactor into a permanently shadowed polar crater and detected at least of water in a plume of ejected material. Another examination of the LCROSS data showed the amount of detected water to be closer to, in May 2011, 615.1410 ppm water in melt inclusions in lunar sample 74,220 was reported. The famous high titanium orange glass soil of volcanic origin collected during the Apollo 17 mission in 1972. The inclusions were formed during explosive eruptions on the Moon approximately 3.7 billion years ago. This concentration is comparable with that of magma in Earth's upper mantle. Although of considerable selenological interest, this announcement affords little comfort to would-be lunar colonists. The sample originated many kilometers below the surface, and the inclusions are so difficult to access that it took 39 years to find them with a state-of-the-art ion microprobe instrument. Gravitational field. The gravitational field of the Moon has been measured through tracking the Doppler shift of radio signals emitted by orbiting spacecraft. The main lunar gravity features are mascons, large positive gravitational anomalies associated with some of the giant impact basins, partly caused by the dense mare basaltic lava flows that fill those basins. The anomalies greatly influence the orbit of spacecraft about the Moon. There are some puzzles. Lava flows by themselves cannot explain all of the gravitational signature, and some mascons exist that are not linked to mare volcanism. Magnetic field. The Moon has an external magnetic field of about 1,100 nanoteslas, less than 1/100th that of Earth. It does not currently have a global dipolar magnetic field, and only has crustal magnetization, probably acquired early in lunar history, when a dynamo was still operating. Alternatively, some of the remnant magnetization may be from transient magnetic fields generated during large impact events through the expansion of an impact-generated plasma cloud in the presence of an ambient magnetic field. This is supported by the apparent location of the largest crustal magnetizations near the antipodes of the giant impact basins. Atmosphere. The Moon has an atmosphere so tenuous as to be nearly vacuum with a total mass of less than. The surface pressure of this small mass is around 3 times 10⁻15 atmospheres. It varies with the lunar day. Its sources include outgassing and sputtering, a product of the bombardment of lunar soil by solar wind ions. Elements that have been detected include sodium and potassium produced by sputtering, helium-4 and neon from the solar wind, and argon-40, radon-222 and polonium-210. Outgassed after their creation by radioactive decay within the crust and mantle. The absence of such neutral species as oxygen, nitrogen, carbon, hydrogen and magnesium, which are present in the regolith, is not understood. Water vapor has been detected by Chandrayaan-1 and found to vary with latitude, with a maximum at approximately 60–70 degrees. It is possibly generated from the sublimation of water ice in the regolith. These gases either return into the regolith due to the Moon's gravity or are lost to space, either through solar radiation pressure or if they are ionized by being swept away by the solar wind's magnetic field. Dust. A permanent asymmetric moon dust cloud exists around the Moon, created by small particles from comets. Estimates are 5 tons of comet particles strike the Moon's surface each 24 hours. The particles strike the Moon's surface, ejecting moon dust above the Moon. The dust stays above the Moon approximately 10 minutes, taking 5 minutes to rise and 5 minutes to fall. On average, 120 kilograms of dust are present above the Moon, rising to 100 kilometers above the surface. The dust measurements were made by LADEE's Lunar Dust Experiment between 20 and 100 kilometers above the surface. During a 6-month period, LDEX detected an average of 0.3 micrometer moon dust particle each minute. Dust particle counts peaked during the Geminid quadrant in northern Taurid and Omicron Centaurid meteor showers when the Earth and Moon pass through comet debris. The cloud is asymmetric, more dense near the boundary between the Moon's day side and night side. Past thicker atmosphere. In October 2017, NASA scientists at the Marshall Space Flight Center and the Lunar and Planetary Institute in Houston announced their finding, based on studies of Moon magma samples retrieved by the Apollo missions, that the Moon had once possessed a relatively thick atmosphere for a period of 70 million years between 3 and 4 billion years ago. This atmosphere, sourced from gases ejected from lunar volcanic eruptions, was twice the thickness of that of present-day Mars. The ancient lunar atmosphere was eventually stripped away by solar winds and dissipated into space. Seasons. The Moon's axial tilt with respect to the ecliptic is only 1.5424 degrees, much less than the 23.44 degrees of Earth. Because of this, the Moon's solar illumination varies much less, with season and topographical details play a crucial role in seasonal effects. From images taken by Clementine in 1994, it appears that 4 mountainous regions on the rim of Perry crater at the Moon's north pole may remain illuminated for the entire lunar day, creating peaks of eternal light. No such regions exist at the South Pole. Similarly, there are places that remain in permanent shadow at the bottoms of many polar craters, and these dark craters are extremely cold. Lunar Reconnaissance Orbiter measured the lowest summer temperatures in craters at the southern pole at and just close to the winter solstice in North Polar Hermite crater. This is the coldest temperature in the solar system ever measured by a spacecraft, colder even than the surface of Pluto. Average temperatures of the Moon's surface are reported, but temperatures of different areas will vary greatly depending upon whether they are in sunlight or shadow. Orbit. The Moon makes a complete orbit around Earth with respect to the fixed stars about once every 27.3 days. However, because Earth is moving in its orbit around the Sun at the same time, it takes slightly longer for the Moon to show the same phase to Earth, which is about 29.5 days. Unlike most satellites of other planets, the Moon orbits closer to the ecliptic plane than to the planet's equatorial plane. The Moon's orbit is subtly perturbed by the Sun and Earth in many small, complex and interacting ways. For example, the plane of the Moon's orbit gradually rotates once every 18.61 years, which affects other aspects of lunar motion. These follow-on effects are mathematically described by Cassini's laws. Relative size. The Moon is exceptionally large relative to Earth, a quarter its diameter and 1/81 its mass. It is the largest moon in the Solar System relative to the size of its planet, though Charon is larger relative to the dwarf planet Pluto at 1/9 Pluto's mass. Earth and the Moon are nevertheless still considered a planet-satellite system rather than a double planet because their barycenter, the common center of mass, is located beneath Earth's surface. Appearance from Earth. The Moon is in synchronous rotation. It rotates about its axis in about the same time it takes to orbit Earth. This results in it always keeping nearly the same face turned towards Earth. However, due to the effect of libration, about 59% of the Moon's surface can actually be seen from Earth. The Moon used to rotate at a faster rate, but early in its history its rotation slowed and became tidally locked in this orientation as a result of frictional effects associated with tidal deformations caused by Earth. With time, the energy of rotation of the Moon on its axis was dissipated as heat, until there was no rotation of the Moon relative to the Earth. The side of the Moon that faces Earth is called the near side and the opposite the far side. The far side is often inaccurately called the dark side, but it is in fact illuminated as often as the near side, once per lunar day. During the new moon phase we observe on Earth when the near side is dark. In 2016, planetary scientists using data collected on the much earlier NASA Lunar Prospector mission found two hydrogen-rich areas on opposite sides of the Moon, probably in the form of water ice. It is speculated that these patches were the poles of the Moon billions of years ago, before it was tidally locked to Earth. The Moon has an exceptionally low albedo, giving it a reflectance that is slightly brighter than that of worn asphalt. Despite this, it is the brightest object in the sky after the Sun. This is partly due to the brightness enhancement of the opposition effect at quarter phase. The Moon is only 1/10 as bright rather than half as bright as at full moon. Additionally, color constancy in the visual system recalibrates the relations between the colors of an object and its surroundings, and because the surrounding sky is comparatively dark, the sunlit Moon is perceived as a bright object. The edges of the full moon seem as bright as the center, with no limb darkening due to the reflective properties of lunar soil, which reflects more light back towards the Sun than in other directions. The Moon does appear larger when close to the horizon, but this is a purely psychological effect known as the Moon illusion, first described in the 7th century BC. The full moon subtends an arc of about 0.52 degrees in the sky, roughly the same apparent size as the Sun. The highest altitude of the Moon in the sky varies with the lunar phase and the season of the year. The full moon is highest during winter. The 18.61-year node cycle also has an influence. When the ascending node of the lunar orbit is in the vernal equinox, The lunar declination can go as far as 28 degrees each month. This means the moon can go overhead, at latitudes up to 28 degrees from the equator instead of only 18 degrees. The orientation of the moon's crescent also depends on the latitude of the observation site. Close to the equator, an observer can see a smile-shaped crescent moon. The moon is visible for 2 weeks every 27.3 days at the North and South Pole. The moon's light is used by zooplankton in the Arctic when the sun is below the horizon for months on end. The distance between the moon and Earth varies from around 2 aperiges and apogees, respectively. On the 14th of November 2016, it was closer to Earth when at full phase than it has been since 1948, 14% closer than its farthest position in apogee, reported as a supermoon. This closest point coincides within an hour of a full moon, and it was 30% more luminous than when at its greatest distance, due to its angular diameter being 14% greater. Because script style 1.14 to the power of 2, approximately 1.30. At lower levels, the human perception of reduced brightness as a percentage is provided by the following formula: text 0 times sqrt when the actual reduction is 1.00, 1.30, or about 0.770. The perceived reduction is about 0.877 or 1.00, 1.14. This gives a maximum perceived increase of 14% between apogee and perigee moons of the same phase. There has been historical controversy over whether features on the moon's surface change over time. Today, many of these claims are thought to be illusory, resulting from observation under different lighting conditions, poor astronomical seeing, or inadequate drawings. However, outgassing does occasionally occur and could be responsible for a minor percentage of the reported lunar transient phenomena. Recently, it has been suggested that a roughly diameter region of the lunar surface was modified by a gas release event about 1 million years ago. The moon's appearance, like that of the sun, can be affected by Earth's atmosphere. Common effects are a 22 degrees halo ring formed when the moon's light is refracted through the ice crystals of high cirrus stratus cloud, and smaller coronal rings when the moon is seen through thin clouds. The illuminated area of the visible sphere is given by 2 sin squared, where E is the elongation, and the sun. Tidal effects. The gravitational attraction that masses have for one another decreases inversely, with the square of the distance of those masses from each other. As a result, the slightly greater attraction that the moon has for the side of Earth closest to the moon, as compared to the part of the Earth opposite the moon, results in tidal forces. Tidal forces affect both the Earth's crust and oceans. The most obvious effect of tidal forces is to cause 2 bulges in the Earth's oceans, one on the side facing the moon, and the other on the side opposite. This results in elevated sea levels called ocean tides. As the Earth spins on its axis, one of the ocean bulges is held in place under the moon, while another such tide is opposite. As a result, there are 2 high tides and 2 low tides in about 24 hours. Since the moon is orbiting the Earth in the same direction of the Earth's rotation, the high tides occur about every 12 hours and 25 minutes. The 25 minutes is due to the moon's time to orbit the Earth. The sun has the same tidal effect on the Earth, but its forces of attraction are only 40% that of the moon's. The sun's and moon's interplay is responsible for spring and neap tides. If the Earth were a water world, it would produce a tide of only 1 meter. And the tide would be very predictable, but the ocean tides are greatly modified by other effects, the frictional coupling of water to Earth's rotation through the ocean floors, the inertia of water's movement, ocean basins that grow shallower near land, the sloshing of water between different ocean basins. As a result, the timing of the tides at most points on the Earth is a product of observations that are explained incidentally by theory. While gravitation causes acceleration and movement of the Earth's fluid oceans, gravitational coupling between the Moon and Earth's solid body is mostly elastic and plastic. The result is a further tidal effect of the Moon on the Earth that causes a bulge of the solid portion of the Earth nearest the Moon that acts as a torque in opposition to the Earth's rotation. This drains angular momentum and rotational kinetic energy from Earth's spin, slowing the Earth's rotation. That angular momentum lost from the Earth is transferred to the Moon in a process which lifts the Moon into a higher orbit and results in its lower orbital speed about the Earth. Thus, the distance between Earth and Moon is increasing and the Earth's spin is slowing in reaction. Measurements from laser reflectors left during the Apollo missions have found that the Moon's distance increases by per year. Atomic clocks also show that Earth's day lengthens by about 15 microseconds every year, slowly increasing the rate at which UTC is adjusted by leap seconds left to run its course. This tidal drag would continue until the spin of Earth and the orbital period of the Moon matched, creating mutual tidal locking between the two. As a result, the Moon would be suspended in the sky over one meridian, as is already currently the case with Pluto and its moon Charon. However, the Sun will become a red giant engulfing the Earth-Moon system long before this occurrence. In a like manner, the lunar surface experiences tides of around amplitude over 27 days, with two components, a fixed one due to Earth because they are in synchronous rotation, and a varying component from the Sun. The Earth-induced component arises from libration, a result of the Moon's orbital eccentricity. Libration also changes the angle from which the Moon is seen, allowing a total of about 59% of its surface to be seen from Earth. Over time, the cumulative effects of stress built up by these tidal forces produces moonquakes. Moonquakes are much less common and weaker than are earthquakes, although moonquakes can last for up to an hour, a significantly longer time than terrestrial quakes, because of the absence of water to damp out the seismic vibrations. The existence of moonquakes was an unexpected discovery from seismometers placed on the Moon by Apollo astronauts from 1969 through 1972. Eclipses. Eclipses can only occur when the Sun, Earth and Moon are all in a straight line. Solar eclipses occur at new moon when the Moon is between the Sun and Earth. In contrast, lunar eclipses occur at full moon when Earth is between the Sun and Moon. The apparent size of the Moon is roughly the same as that of the Sun, with both being viewed at close to 1/2 degree wide. The Sun is much larger than the Moon, but it is the precise vastly greater distance that gives it the same apparent size as the much closer and much smaller Moon from the perspective of Earth. The variations in apparent size due to the non-circular orbits are nearly the same as well, though occurring in different cycles. This makes possible both total and annular solar eclipses. In a total eclipse, the Moon completely covers the disk of the Sun, and the solar corona becomes visible to the naked eye, because the distance between the Moon and Earth is very slowly increasing. Over time, the angular diameter of the Moon is decreasing. Also, as it evolves toward becoming a red giant the size of the Sun and its apparent diameter in the sky are slowly increasing. The combination of these two changes means that hundreds of millions of years ago, the Moon would always completely cover the Sun on solar eclipses, and no annular eclipses were possible. Likewise, hundreds of millions of years in the future, the Moon will no longer cover the Sun completely and total solar eclipses will not occur. because the Moon's orbit around Earth is inclined by about 5.145 degrees to the orbit of Earth around the Sun. Eclipses do not occur at every full and new moon. For an eclipse to occur, the Moon must be near the intersection of the two orbital planes. The periodicity and recurrence of eclipses of the Sun by the Moon and of the Moon by Earth is described by the Saros, which has a period of approximately 18 years. Because the Moon is continuously blocking our view of the half-degree wide circular area of the sky. The related phenomenon of occultation occurs when a bright star or planet passes behind the Moon and is occulted, hidden from view. In this way, a solar eclipse is an occultation of the Sun. Because the Moon is comparatively close to Earth, occultations of individual stars are not visible everywhere on the planet nor at the same time. Because of the precession of the lunar orbit, each year different stars are occulted. Ancient and medieval studies. Understanding of the Moon's cycles was an early development of astronomy. By the Babylonian astronomers had recorded the 18-year Saros cycle of lunar eclipses, and Indian astronomers had described the Moon's monthly elongation. The Chinese astronomer Shi Shen gave instructions for predicting solar and lunar eclipses. Later, the physical form of the Moon and the cause of moonlight became understood. The ancient Greek philosopher Anaxagoras reasoned that the Sun and Moon were both giant spherical rocks, and that the latter reflected the light of the former. Although the Chinese of the Han Dynasty believed the Moon to be energy equated to qi, their radiating influence theory also recognized that the light of the Moon was merely a reflection of the Sun, and Jing Fang noted the sphericity of the Moon. In the 2nd century AD, Lucian wrote a novel where the heroes travel to the Moon, which is inhabited. In 499 AD, the Indian astronomer Aryabhata mentioned in his Aryabhatya that reflected sunlight is the cause of the shining of the Moon. The astronomer and physicist Alhazen found that sunlight was not reflected from the Moon like a mirror, but that light was emitted from every part of the Moon's sunlit surface in all directions. Shen Kuo of the Song dynasty created an allegory equating the waxing and waning of the Moon to a round ball of reflective silver that, when doused with white powder and viewed from the side, would appear to be a crescent. In Aristotle's description of the universe, the Moon marked the boundary between the spheres of the mutable elements and the imperishable stars of ether, an influential philosophy that would dominate for centuries. However, in the Seleucus of Seleucia correctly theorized that tides were due to the attraction of the Moon, and that their height depends on the Moon's position relative to the Sun. In the same century, Aristarchus computed the size and distance of the Moon from Earth, obtaining a value of about 20 times the radius of Earth for the distance. These figures were greatly improved by Ptolemy, his values of a mean distance of 59 times Earth's radius and a diameter of 0.292 Earth diameters were close to the correct values of about 60 and 0.273 respectively. Archimedes designed a planetarium that could calculate the motions of the Moon and other objects in the solar system. During the Middle Ages, before the invention of the telescope, the Moon was increasingly recognized as a sphere, though many believed that it was perfectly smooth. In 1609, Galileo Galilei drew one of the first telescopic drawings of the Moon in his book, and noted that it was not smooth but had mountains and craters. Telescopic mapping of the Moon followed, later in the 17th century. The efforts of Giovanni Battista Riccioli and Francesco Maria Grimaldi led to the system of naming of lunar features in use today. The more exact 1834-36 of Wilhelm Beer and Johann Heinrich Madler and their associated 1837 book, the first trigonometrically accurate study of lunar features, included the heights of more than 1,000 mountains and introduce the study of the Moon at accuracies possible in earthly geography. Lunar craters first noted by Galileo were thought to be volcanic until the 1870s proposal of Richard Proctor that they were formed by collisions. This view gained support in 1892 from the experimentation of geologists Grove, Carl Gilbert and from comparative studies from 1920 to the 1940s, leading to the development of lunar stratigraphy, which by the 1950s was becoming a new and growing branch of astrogeology. Soviet missions. The Cold War-inspired space race between the Soviet Union and the US led to an acceleration of interest in exploration of the Moon. Once launches had the necessary capabilities, these nations sent uncrewed probes on both flyby and impact lander missions. Spacecraft from the Soviet Union's lunar program were the first to accomplish a number of goals, following 3 unnamed failed missions in 1958. The first human-made object to escape Earth's gravity and pass near the Moon was Lunar 1. The first human-made object to impact the lunar surface was Lunar 2. And the first photographs of the normally occluded far side of the Moon were made by Lunar 3. All in 1959. The first spacecraft to perform a successful lunar soft landing was Lunar 9. And the first uncrewed vehicle to orbit the Moon was Lunar 10, both in 1966. Rock and soil samples were brought back to Earth by 3 lunar sample return missions, which returned 0.3 kilograms total. 2 pioneering robotic rovers landed on the Moon in 1970 and 1973 as a part of Soviet Lunar Cod program. United States missions during the late 1950s at the height of the Cold War. The United States Army conducted a classified feasibility study that proposed the construction of a manned military outpost on the Moon called Project Horizon, with the potential to conduct a wide range of missions from scientific research to nuclear Earth bombardment. The study included the possibility of conducting a lunar-based nuclear test. The Air Force, which, at the time, was in competition with the Army for a leading role in the space program, developed its own similar plan called LUNEX. However, both these proposals were ultimately passed over as the space program was largely transferred from the military to the civilian agency NASA. Following President John F. Kennedy's 1961 commitment to a crewed moon landing before the end of the decade, the United States, under NASA leadership, launched a series of uncrewed probes to develop an understanding of the lunar surface in preparation for crewed missions. The Jet Propulsion Laboratory's Ranger program produced the first close-up pictures. The Lunar Orbiter program produced maps of the entire Moon. The Surveyor program landed its first spacecraft 4 months after Lunar 9. The crewed Apollo program was developed in parallel, after a series of uncrewed and crewed tests of the Apollo spacecraft in Earth orbit, and spurred on by a potential Soviet lunar flight in 1968. Apollo 8 made the first crewed mission to lunar orbit. The subsequent landing of the first humans on the Moon in 1969 is seen by many as the culmination of the space race. Neil Armstrong became the first person to walk on the Moon as the commander of the American mission Apollo 11, by first setting foot on the Moon at 2:56 Coordinated Universal Time on 21 July 1969. An estimated 500 million people worldwide watched the transmission by the Apollo TV camera, the largest television audience for a live broadcast at that time. The Apollo missions 11 to 17 returned 837.87 pounds of lunar rock and soil in 2,196 separate samples. The American moon landing and return was enabled by considerable technological advances in the early 1960s in domains such as ablation chemistry, software engineering and atmospheric re-entry technology, and by highly competent management of the enormous technical undertaking. Scientific instrument packages were installed on the lunar surface during all the Apollo landings. Long-lived instrument stations including heat-flow probes, seismometers and magnetometers were installed at the Apollo 1, 2, 1, 4, 1, 5, 1, 6 and 17 landing sites. Direct transmission of data to Earth concluded in late 1977 due to budgetary considerations. But as the station's lunar laser ranging corner cube retroreflector arrays are passive instruments, they are still being used. Ranging to the stations is routinely performed from Earth-based stations with an accuracy of a few centimeters, and data from this experiment are being used to place constraints on the size of the lunar core. 1980s 2000. After the first moon race there were years of near quietude, but starting in the 1990s, many more countries have become involved in direct exploration of the moon. In 1990, Japan became the third country to place a spacecraft into lunar orbit with its Titan spacecraft. The spacecraft released a smaller probe Hagoromo in lunar orbit, but the transmitter failed, preventing further scientific use of the mission. In 1994, the U.S. sent the Joint Defense Department (NASA) spacecraft Clementine to lunar orbit. This mission obtained the first near-global topographic map of the Moon, and the first global multispectral images of the lunar surface. This was followed in 1998 by the Lunar Prospector mission, whose instruments indicated the presence of excess hydrogen at the lunar poles, which is likely to have been caused by the presence of water ice in the upper few meters of the regolith within permanently shadowed craters. India, Japan, China, the United States, and the European Space Agency each sent lunar orbiters, and especially ISRO's Chandrayaan-1 has contributed to confirming the discovery of lunar water ice in permanently shadowed craters at the poles and bound into the lunar regolith. The post-Apollo era has also seen two rover missions, the final Soviet Lunar Cod mission in 1973, and China's ongoing Chang'e 3 mission, which deployed its U-2 rover on 14 December 2013. The Moon remains under the Outer Space Treaty, free to all nations to explore for peaceful purposes. 21st century. The European spacecraft Smart 1, the second ion-propelled spacecraft, was in lunar orbit from 15 November 2004 until its lunar impact on 3 September 2006, and made the first detailed survey of chemical elements on the lunar surface. The ambitious Chinese lunar exploration program began with Chang'e 1, which successfully orbited the Moon from 5 November 2007 until its controlled lunar impact on 1 March 2009. It obtained a full image map of the Moon. Chang'e 2, beginning in October 2010, reached the Moon more quickly, mapped the Moon at a higher resolution over an 8-month period, then left lunar orbit for an extended stay at the Earth-Sun L2 Lagrangian point, before finally performing a flyby of asteroid 4179 to Tartus on 13 December 2012, and then heading off into deep space. On 14 December 2013, Chang'e 3 landed a lunar lander onto the Moon's surface, which in turn deployed a lunar rover named U-2. This was the first lunar soft landing since Lunar 24 in 1976. And the first lunar rover mission since Lunar Cod 2 in 1973. China intends to launch another rover mission before 2020, followed by a sample return mission soon after. Between 4 October 2007 and 10 June 2009, the Japan Aerospace Exploration Agency's Kaguya mission, a lunar orbiter fitted with a high-definition video camera and 2 small radio transmitter satellites obtained lunar geophysics data, and took the first high-definition movies from beyond Earth orbit. India's first lunar mission, Chandrayaan-I, orbited from the 8th of November 2008 until loss of contact on the 27th of August 2009, creating a high-resolution chemical, mineralogical and photogeological map of the lunar surface, and confirming the presence of water molecules in lunar soil. The Indian Space Research Organisation planned to launch Chandrayaan-2 in 2013, which would have included a Russian robotic lunar rover. However, the failure of Russia's Phobos Grunt mission has delayed this project. The U.S. co-launched the Lunar Reconnaissance Orbiter and the LCROSS Impactor and Follow-up Observation Orbiter on 18 June 2009. LCROSS completed its mission by making a planned and widely observed impact in the crater Cabeus on 9 October 2009, whereas LRO is currently in operation obtaining precise lunar altimetry and high-resolution imagery. In November 2011, the LRO passed over the large and bright Aristarchus crater. NASA released photos of the crater on 25 December 2011. 2 NASA Grail spacecraft began orbiting the Moon around 1 January 2012 on a mission to learn more about the Moon's internal structure. NASA's LADEE probe, designed to study the lunar exosphere, achieved orbit on 6 October 2013. Upcoming lunar missions include Russia's Lunar Globe, an uncrewed lander with a set of seismometers, and an orbiter based on its failed Martian Phobos Grunt mission. Privately funded lunar exploration has been promoted by the Google Lunar X Prize, announced 13 September 2007, which offers $20 million to anyone who can land a robotic rover on the Moon and meet other specified criteria. Shackleton Energy Company is building a program to establish operations on the south pole of the Moon to harvest water and supply their propellant depots. NASA began to plan to resume crewed missions following the call by U.S. President George W. Bush on 14 January 2004. For a crewed mission to the Moon by 2019 and the construction of a lunar base by 2024. The Constellation program was funded and construction and testing begun on a crewed spacecraft and launch vehicle and design studies for a lunar base. However, that program has been cancelled in favor of a crewed asteroid landing by 2025 and a crewed Mars orbit by 2035. India has also expressed its hope to send a crewed mission to the Moon by 2020. Planned commercial missions. In 2007, the X Prize Foundation together with Google launched the Google Lunar X Prize to encourage commercial endeavors to the Moon. A prize of $20 million will be awarded to the first private venture to get to the Moon with a robotic lander by the end of March 2018, with additional prizes worth $10 million for further milestones. As of August 2016, 16 teams are participating in the competition. In August 2016, the U.S. government granted permission to U.S.-based startup Moon Express to land on the Moon. This marked the first time that a private enterprise was given the right to do so. The decision is regarded as a precedent helping to define regulatory standards for deep space commercial activity in the future, as thus far companies' operation had been restricted to being on or around Earth. Astronomy from the Moon. For many years the Moon has been recognized as an excellent site for telescopes. It is relatively nearby. Astronomical seeing is not a concern. Certain craters near the poles are permanently dark and cold and thus especially useful for infrared telescopes, and radio telescopes on the far side would be shielded from the radio chatter of Earth. the lunar soil, although it poses a problem for any moving parts of telescopes, can be mixed with carbon nanotubes and epoxies, and employed in the construction of mirrors up to 50 meters in diameter. A lunar zenith telescope can be made cheaply with ionic liquid. In April 1972, the Apollo 16 mission recorded various astronomical photos and spectra in ultraviolet with a far ultraviolet camera spectrograph. Legal status. Although lunar landers scattered pennants of the Soviet Union on the Moon and U.S. flags were symbolically planted at their landing sites by the Apollo astronauts, no nation claims ownership of any part of the Moon's surface. Russia and the U.S. are party to the 1967 Outer Space Treaty, which defines the Moon and all outer space as the province of all mankind. This treaty also restricts the use of the Moon to peaceful purposes, explicitly banning military installations and weapons of mass destruction. The 1979 Moon Agreement was created to restrict the exploitation of the Moon's resources by any single nation, but as of 2014 it has been signed and ratified by only 16 nations, none of which engages in self-launched human space exploration or has plans to do so. Although several individuals have made claims to the Moon in whole or in part, none of these are considered credible. Mythology. A 5,000-year-old rock carving at North Island may represent the Moon, which would be the earliest depiction discovered. The contrast between the brighter highlands and the darker Maria creates the patterns seen by different cultures as the man in the moon, the rabbit and the buffalo, among others. In many prehistoric and ancient cultures, the moon was personified as a deity or other supernatural phenomenon, and astrological views of the moon continue to be propagated today. In the ancient Near East, the moon god was masculine. In Greco-Roman mythology, sun and moon are represented as male and female respectively. The crescent shape, from an early time, was used as a symbol representing the moon. The moon goddess Selene was represented as wearing a crescent on her headgear in an arrangement reminiscent of horns. The star and crescent arrangement also goes back to the Bronze Age, representing either the sun and moon or the moon and planet Venus in combination. It came to represent the goddess Artemis or Hecate, and via the patronage of Hecate came to be used as a symbol of Byzantium, an iconographic tradition of representing sun and moon, with faces developed in the late medieval period. The splitting of the moon is a miracle attributed to Muhammad. Calendar. The moon's regular phases make it a very convenient timepiece, and the periods of its waxing and waning form the basis of many of the oldest calendars. Tally sticks, notched bones dating as far back as 20–30,000 years ago, are believed by some to mark the phases of the moon. The approximately 30-day month is an approximation of the lunar cycle. The English noun month and its cognates in other Germanic languages stem from Proto-Germanic mnth, which is connected to the above-mentioned Proto-Germanic non, indicating the usage of a lunar calendar among the Germanic peoples prior to the adoption of a solar calendar. The pi root of moon h1 not derives from the pi verbal root mer1 to measure, indicating a functional conception of the moon, i.e., marker of the month, and echoing the moon's importance to many ancient cultures in measuring time, or meaning month. Most historical calendars are lunisolar. The 7th century Islamic calendar is an exceptional example of a purely lunar calendar. Months are traditionally determined by the visual sighting of the hilal, or earliest crescent moon, over the horizon. Modern art and literature. The moon has been the subject of many works of art and literature, and the inspiration for countless others. It is a motif in the visual arts, the performing arts, poetry, prose and music. Lunacy. The moon has long been associated with insanity and irrationality. The words lunacy and lunatic are derived from the Latin name for the moon, Luna. Philosophers Aristotle and Pliny the Elder argued that the full moon induced insanity in susceptible individuals, believing that the brain, which is mostly water, must be affected by the moon and its power over the tides, but the moon's gravity is too slight to affect any single person. Even today, people who believe in a lunar effect claim that admissions to psychiatric hospitals, traffic accidents, homicides or suicides increase during a full moon. But dozens of studies invalidate these claims. Brought to you by WikiVidi.com. Would you like to know more?